Let's load our data. These are our images containing 1s, 2s, 3s, and all this. So we load our data containing the images of different numbers, handwritten numbers. First, we load the packages. We load the data. This is not a complete data set. I chose randomly 5,000. And that is because to speed it up a little bit. And what I want you to do is compare the two of the images, the first image and the second image. How would I compare them? Well, first I have to wait until they load. Here they are. So these are the pixels of the image. Each pixel can either be bright, white would be 255, or it can be black, then the value is 0, or it can be anything in between. So what I do is I compare, let's say, the image number 1, which is in the first row, and the image number 2. And to calculate, let's say, the Manhattan distance, I calculate the difference. No difference, 0, 0, 0, 0, 0. Why is that? Well, I'm on the top of the image where everything is black in both images. If I go a little further, then I find data here. For example, this one in this pixel has 25 and this one is 0. So I add 25 to my Manhattan distance. I add 131 to my Manhattan distance. Let's go on. I'm just comparing the first one. Here, in this pixel, the first image has an 88, so it's dark gray. The second one is almost white, 253. I take the difference, I add it to my Manhattan distance. And if I do that for all my 700 pixels, I have a measure for how different they are in terms of Manhattan distance. If I use the Euclidean distance, I do the same thing. I calculate the distance like before, but I square it. I add up all my squares, calculate the square root, I have my Euclidean distance. I hope you see how you can compare two images to see if they are different and how different they are. This is how I try to find my nearest neighbor. So, I set my random number generator. I split the data set into training data and testing data. I just established the rule here. It's not the actual split. But now I generate my recipe. And the data need to be manipulated only in a very short way. The recipe is always, almost always based on the training data. That's why I have this one here. And I make the label. This is the first row that shows actually what the image actually displays, 1 or 2 or 3. So we can double check. I make that a factor. Again, a factor is something like a dummy variable. It's just differently stored internally in R. And most classification procedures need a dummy variable. So I do that here. I apply this recipe to the training data by juicing it, because the data are already in the recipe for the training data. I just have to squeeze them out. I apply it now to a new data set, to the testing data. And that's command for that. If I use the new data is bake, did that already. And now I run my k nearest neighbor, basically comparing every record to every other record and find the nearest neighbor for each of the records. And I only go for the nearest neighbor. I don't go for the 10 nearest neighbor. I just go for the nearest neighbor. Okay, it takes a moment. I think it takes about a minute. And think about, I have 5,000 records. So I compare each of these records to each of the other ones. So I get a lot of comparison to do here.
Professor, I have a question.
Yes, go ahead.
What would happen if the neighbor's value was not one? Like, let's say it was 5 or something. How would that change the algorithm?
We will do that later on, but I can tell you already, it would still compare each neighbor to each neighbor. But when I say, okay, what is the nearest neighbor? I don't pick the nearest neighbor, I pick the 5 nearest neighbors. So I take the 5 values that have the smallest distance. And then obviously the question arises, okay, what if these 5 values don't show the same result? Then I have a vote. Does that make sense?
Yeah, I think I can see it. Yeah.
And what is obvious is I just said nearest neighbor is 1 because it's the easiest one. But what is a legitimate question is, well, is neighbor 1 really the best one? Maybe it's neighbor 10 or neighbor 20 or neighbor 5. So I have to tune the model, and we will do that later on. Basically, I try them all and find out where I get the best results.
Okay, thank you.
Yeah, okay. So this is not really necessary here, but I take a few of the images. I show the images, so I get them back into a format. I take the first row for image 1, but get it back into a format that I can actually display. And here it is. This is how it was written. It's obviously an 8, and I can see it here. The label showed 8, which was hidden in the image, and our system actually predicted 8. And I can do that for other ones. Here's a 1 that is predicted correctly. So this gives you an idea, and I think you can do that at home. I don't want to waste a lot of time on it. But how well does our system do based on the testing data that we have not used to find the nearest neighbor? So now we push a testing record and find its nearest neighbor. And then the next testing record and find its nearest neighbor and predict. And we do that for all our testing records. We have a total of about 500 testing records here. And how do we do that? Well, we use a model that we built already. And we use it here as a first parameter to predict. And the new data set is the test data set. If we do that with this predict command, we will get 500 predictions. Well, in order to see if these 500 predictions are correct, we have to compare them to the true results. The true results are in the test data set. So we bind our predictions here, the columns from there, with the ones of the testing data set. And then if we have the truths and the predictions, we can use the command confusion matrix, conf underline matrix, mat. We just have to tell the command what is the truth. The truth is in the label, and the predictions are in the class. If I don't do that here, if I just execute this command incompletely, you will see. Takes a moment. This is not our confusion matrix because I did it incompletely, but see, we have now a matrix that has the variable dot predict class. Treat the dot like any other letter. The predicted value is 8. The label was 8. You see, in most cases, it's right. Here, the predicted value was 4, and the label was 4. So to get that into a confusion matrix, the only thing what we have to do, we push these results to the command confusion matrix, and we tell the command, you find the truth in the variable label, you find the estimate in the variable dot predict. If I execute it, again, it takes a moment, and I get the result. I generate a confusion matrix. The results for the confusion matrix are saved in the variable confusion matrix test. I can print my confusion matrix, and it shows the predictions were pretty good. Here's the truth. The confusion matrix is a little bit more interesting than it was before because it has now 10 columns with the truths here. When it was truly a 0, in 52 cases it was predicted as a 0. In 2 cases it was predicted as a 5. In 1 case it was predicted as a 1. And you can see the correct predictions are always on the diagonal. Here, when it was a 1, it was predicted as a 1 in 60 cases. And this is obviously wrong because it was a 1, but it was predicted as a 2. So we can see here the results on the diagonal are pretty large in number compared to the other. So it seems to be a good quality. Seems to be is probably not enough. We can analyze this matrix with a summary result. And we only look here at the accuracy. 90% of the results were predicted correctly. That's not bad. Can we improve that? The answer is yes. We can improve that because, and that was the question, I forgot who it was. Somebody asked already about it. Do we always have to take 1? Like I did here. Do we always have to take 1? And the answer is no, we don't. We can use other values. So to reiterate, if we use other values, if we have, for example, k like 5 here, I could run it and see what's my accuracy. Then I could run 10 and see what my accuracy. And I can run 20 and so on and so on, except that this would be a pain. And I would have to keep track of the results, and then I fit the best neighbor. So what we do instead, we use our tuning tools. So I load tidy models. I load the tidyverse. Load my data. I split them in training and testing data. Generate my testing results. And now I create my model, but look at it. At neighbors where I had before, the 1, I have now the placeholder, tune. That means, well, find out. That's the only hyperparameter I'm tuning. So I determine my folds. I want 6 folds. And what do I want to try? My tuning grid is the neighbors should be 1, 5, 10, and 20. You can put whatever you want here. I played around a little bit before. If you put in more values, it obviously takes longer. You can probably put in like 10 or 15 or even 20 values. Then it would take about a night, but we don't want to wait forever. So I put in 4 values. I define my folds. I did that already. Tuning grid. And because I'm curious how long it takes, I will test the time. I store the start time here. I don't have to do it. And I run my simulation. And while it runs, I can explain what is happening here. So I created 6 folds. Basically, I split my training data into 6 equal parts. And then I run my first scenario, k equals 1. That's the one that's currently running. When I run that scenario, I run it the first time using fold number 1. Remember, I had 6 folds of the training data as an assessment fold. It's basically the one that tests the quality, and the 5 other ones to train. I get a result, an accuracy. An accuracy for my first scenario and for my first, based on the quality of the first fold. Now I run the same scenario again, k equals 1. And what I do is I now use from my folds the second fold to estimate the quality, and to train the model, I use folds number 1, 3, 4, 5, and 6. I do that again and again. I use the second fold, the third fold, and so on and so on. How far are we here? This one does it a little bit different, but just the order is different. It uses the first fold here as an assessment fold and runs scenario number 1, scenario number 2, 3, and 4. So we're at the second fold. We have to go all the way to the 6th fold, and then it will be done. It takes about a while, about 20 minutes, I think. And I don't want to bore you for 20 minutes, so I just let it run here, and we come back to it. It is done meanwhile. All the programs, all the ones are processed. So we had 4 different scenarios. We tried a K of 1, a 15, 0, and 20. We have 6 different folds. So there were 24 runs through the program. So let's look at the results. And let's look at them. It has our 4 scenarios, 1, K1, 5, 10, and whatever. And it reports the accuracy here, but not the accuracy for each fold. This is just the average from the folds. And we had 6 folds here. So we can see the accuracy here for 1 was about 88%. For 5 was about 88%. By the way, the same accuracy, probably because the same prediction was made. When you have 10 folds, we can see the accuracy goes up to 89.2. If we have 20 folds, the accuracy goes down. So 10 folds is our best result here. Well, instead of writing this down, we can find it, just select the best parameter. So K10 is safe. And then we just run the matrix, then we run the model again with the best parameter, which basically means we run it with K equal 10. So for each record, we try to classify. For each image in the testing data set, we try to classify. We find the 10 images that are closest to it, the 10 most similar images. And then we have a vote. The number that applies most of it, let it be a 0, a 1, a 2, or 3 in these 10 images, will be our prediction. If it's a par, we just flip a coin. We wait a moment, it doesn't take forever. There it is. We run the confusion matrix again, and I don't have to explain it to you because it's the same thing. The most important thing is the predict command. We use our model, and we use the best model. See, this is saved here. And we make the predictions. We compare to the truth. We get our confusion matrix. And it takes a moment. We print the confusion matrix. It's still good. Is it better than we had before? Based on our test data, yeah, we could improve from 90% to 92%. Interesting enough, we got a little bit better data accuracy in our test data than we got in the training data. Normally, the test data would be a little bit worse because they were not used for training. But with some dumb luck, and we have this dumb luck here, they might be even better than the training data. So that's it for today. I have to do a lot of cutting for the recording, but I will make the recording available.